Good morning. Thanks very much to the organisers for inviting me here today. It's a pleasure to address this audience. My name's Ian Scott. I founded Moltex Energy back in 2014 along with John Durham, who at that time was the founder of the Alvin Weinberg Foundation, set up with the vision of commercialising molten salt reactors, and that is exactly what we are setting out to do. The mission of Moltex is quite explicitly financial. We believe that nuclear energy will only make a real consequence to solving the global warming problem if it can be brought down to a cost where it is cheaper to use nuclear than it is to burn coal and gas. And subsidies can get you started, but you will not achieve real global penetration without that cost advantage. And that is what Moltex Energy is all about. This slide should be a very frightening slide to anybody listening to this. This is from the 2019 World Energy Outlook from the International Energy Agency. And it's worth looking at the curves here. There's some very good news on here. Solar photovoltaic and wind power are both projected to grow to be very substantial parts of the world's energy production by 2040. That's where the good news ends, however. If you look at the curves of this graph for coal, all that's projected is that we will stop getting worse in our coal burning. That is just not good enough. It also shows that burning natural gas will continue to accelerate and virtually double over the period of time. So, in terms of climate change, this is very, very bad news. And this is realistic projections based on current technologies and current policies. The really depressing thing on this slide is the yellow curve at the bottom shows nuclear, which shows nuclear not increasing in any meaningful way in terms of total gigawatts of capacity. This is not what the world needs. So why is this happening? Why is the great promise of nuclear energy not being fulfilled? There's really two reasons. And this is a slide which is deliberately provocative. The twin drivers of the slow death of nuclear energy, because that is what we are facing now. The first driver is massive increase in the capital cost. This is not news, but it is challenging the basic economics of reactors. There's a very good study came out from the EPRI in the USA looking at how nuclear's penetration in the USA would evolve at different capital price points. The message is very simple. If you can get your overnight capital cost down to $2,000 per kilowatt, then nuclear becomes a dominant power source. At $3,000 per kilowatt, nuclear becomes a significant contributor to power. Above that, and nuclear is essentially irrelevant and will not grow, will not roll out. Where are we compared to that? That $3,000 threshold for viability? Well, new pressurised water reactors are running at $7,000 to $8,000 per kilowatt and counting. That number is going up all the time. So that is only one part of the story. The second important factor, which is just as important as cost, is that the electricity markets are changing as renewables become cheaper and cheaper and penetrate deeper and deeper into markets. Renewables generate power at zero marginal cost, and that means that they will produce whatever the market says. As a result, there are times when baseload demand is entirely met by renewables, and there is simply no need for a power generation source which is always producing 24 hours a day, 7 days a week. You need a power source which can produce 24/7, but a power source that must produce 24/7 faces economic disaster. This slide is one that I have shamelessly borrowed, stolen from Charles Forsberg. He showed it some years ago. It shows the pictures on a particular day in Southern California of wholesale prices of electricity. And they showed it in 2012 in red and 2017 in blue. What's happened between 2012 and 2017 was a major rollout of solar power. And the consequence has been that around the middle of the day, prices were going negative. Generators were literally paying the grid operator to take their power. That's not a great business proposition. That's getting worse. I'd like to show you some data from the UK now. This is for a full week period towards the end of May of this year. This was a period in May when the wind was blowing, the sun was shining. It was actually a very pleasant week. On the 22nd of May, the average day-ahead price for electricity was minus £9.92 a megawatt hour. So generators were paying that much for every megawatt hour that they produced. In fact, at one point in the early hours that day, the price reached minus £52 per megawatt hour. The graph shows you the rate. There's substantial periods of time when prices are very, very substantially negative. So who's paying these negative prices? Well, two people, two organisations. One is nuclear. Nuclear cannot turn itself off quickly. The cost of coming back to power is too great. So nuclear will pay to have its power taken away. And the other contributor there are renewables who have strike prices. If they get guaranteed that we'll be paid £50 per megawatt hour and they have to pay the grid £49 per megawatt hour to take the power away, they're still making £1. They will still produce, even though it's being produced at a clear loss. Such is the power of subsidies. So, put these two things together, and what is the real challenge that nuclear has to address? We need it to have a low enough capital and fixed operating costs so it is profitable when it runs at between 30 and 50% capacity, and to be profitable in direct competition with unsubsidised fossil fuels. That's the target. And today nuclear is nowhere near achieving that target. So let me talk about capital cost. It will come as no surprise to this audience that the primary driver of costs in nuclear is actually safety. This is an interesting graph. I've used it for many years. It shows the overnight capital costs in constant 2014 money by date of completion of nuclear reactors. And up to about 1982, nuclear reactors were running at around $2,000 per kilowatt capital cost. Perfectly viable, well under that $3,000 viability threshold, which is why they rolled out in very large numbers. After 1983, and the problems of Chernobyl in particular and 3 Mile Island, costs skyrocketed. And today, you are running at costs 7,000 to 8,000, which is simply not a viable proposition. The key to eliminating hazards from nuclear reactors is actually molten salts. At two levels. This slide shows my very simplified description of a pressurized water reactor. You have a black pressure vessel on the outside, water inside at high temperature and pressure, and inside that you have tubes containing pellets of uranium oxide fuel. So let's start with the solid fuel pellets. These are remarkably finely engineered structures. They trap the fission gases inside the pores of the fuel. And you have something like 50 volumes of fission gas to every volume of pellet. And the pellets are about 95% solid with only 5% void. That means you're looking at internal pressures of many hundreds of bar. And the pellets hold those in extraordinarily effectively until they don't. And when they don't is when they reach about 1400 degrees centigrade, long short of any meltdown condition, at which point those pellets fall apart catastrophically release large amounts of gas, rupture the tubes they're in, and release that highly radioactive gas into whatever containment you have around it. That's a fundamental hazard. We then take those intrinsically quite dangerous fuel pellets, we put them into a vessel surrounded by water at 300 degrees centigrade, which will, in the event of a pressure vessel failure, explode itself quite catastrophically. Boiler explosions are among the worst industrial accidents in history. Molten salts address this problem at two levels. In the fuel, they do not accumulate the fission product gases, and the most dangerous fission product gases, cesium and iodine, are not gases at all. They are stable salts, and they are only volatile when the salt actually boils. The second area you use molten salts is as the coolant. Replacing water with a molten salt coolant means that you have a coolant which is chemically stable, operates at atmospheric pressure, is not chemically reactive. At a stroke, you have eliminated two of the most important fundamental hazards of the reactor. So, there are essentially two ways that you can use molten salt fuel in a reactor. First way, shown on this slide, is what I call conventional MSRs, molten salt reactors. These are molten salt reactors based around the molten salt reactor experiment done back in the 1950s and 1960s. And the principle is that the fuel and the coolant are the same liquid. So the heat is generated in the liquid fuel. The liquid fuel is then pumped out of the reaction chamber where it was critical into heat exchangers where hopefully it's not critical anymore, and it passes the heat to do something useful with. Apparently relatively simple in principle. That means you are pumping an extraordinarily radioactive liquid at pressure around a relatively complex system with pumps, valves, heat exchangers, welded joints. And unless you've managed to produce the first plumbing system on the planet that can never spring a leak, you have to assume at some point there will be a leak. And then what do you do? It's a problem. It's not necessarily an insoluble problem, but engineering-wise, it's a very difficult problem. The second way, shown on the right-hand side of the slide, is the stable salt reactor technology platform. And this is the simple concept that you put the fuel salt into fuel tubes, rather similar to the fuel tubes used in conventional reactors. We're essentially replacing the uranium oxide with a molten salt. This is, believe it or not, a radically new concept. The patent was filed in 2014. It is now granted in most of the major jurisdictions worldwide. It is genuinely novel. It has sailed through the patent process with very, very little difficulty. It seems extraordinary that idea could actually be novel, but it is. And the reason it's novel is that it was actually considered back in the 1950s by the precursor of the molten salt reactor experiment, who considered putting molten salt fuel in fuel pins because it's a pretty obvious thing to do. They concluded that it didn't work. And the reason they concluded it didn't work was that molten salts are actually quite poor conductors of heat. And they calculated that you couldn't get the heat out from molten salt. However, what is not in the published literature is that their conclusion was based on ignoring convection as a heat transfer process in molten salts. And heat transfer in liquids is dominated by convection. They made that assumption for a good reason. They were designing an aircraft powering nuclear reactor, and that would have to be largely independent of the force and direction of gravity. And so they had to ignore gravity and therefore ignore convection. That decision was never revisited when people gave up on the idea of putting nuclear reactors into aeroplanes, until we reconsidered that 6 years ago. Okay, so this is a platform technology. Putting molten salt in tubes in a reactor is the basic platform technology. There are two implementations of that platform that Moltex is currently working on. First is a fast spectrum reactor that we call the SSR-W, where W stands for Wasteburner. It's a reactor which is fueled by higher actinides recovered from conventional nuclear fuel. It's a chloride salt fuel. It uses a zirconium fluoride based coolant salt. It operates continuously with on-power refueling, and it has completely passive emergency heat removal to the atmosphere. I'll talk a bit more about that reactor. The second one, which I'll say much less about, is a thermal spectrum version fueled by less than 5% low enriched uranium, conventional fuel supply, graphite moderated, but uniquely I think among molten salt reactors the graphite does not contact the fuel. The fuel is a uranium sodium fluoride salt mixture. The coolant salt is proprietary. I'm sorry I can't share what that is with you at this time. It has a very high output temperature, greater than 800 degrees centigrade, and again it has entirely passive emergency heat removal. I won't say any more about the SSR-W, the thermal spectrum reactor, at this stage. So we founded this company in 2014. Progress on developing the SSR-W since then has been quite rapid. The master patent was filed in 2014 and granted in 2014, the same year the company was founded, which is unusual. By 2018, we had established Moltex Energy Canada and granted that company exclusive rights to the SSR-W technology in North America. That same year, we signed an agreement with New Brunswick Power, leading to the development and deployment of this reactor at their Point-le-Preau nuclear power plant site. Since then, we've been working hard with the CNSC. We have almost completed the vendor design review. That will be completed this year, phase 1. We've received major investments from both established nuclear companies, and we are getting significant support from the Canadian government sources. And we've also received very significant funding from the US ARPA-E research grants in the USA. So we have work going on at the US laboratories paid for very generously by the US government, which is a significant help both financially, and there is some really excellent expertise there. But I will say a little about the actual design of the SSR-W reactor. The fuel salt is a uranium plutonium chloride based fuel salt. The coolant salt, as I said before, is a zirconium fluoride potassium fluoride based salt. That salt is in fuel tubes. The fuel tubes are vented. This is not a completely novel concept. This was done with a sodium fast reactor at Dunleary in Scotland back in the 1970s. The reason that it is viable in this reactor is that the off gas is actually really very benign, because the cesium, iodine and most of the fission products are non-volatile. The fuel assemblies are hexagonal. They resemble conventional fast reactor fuel assemblies quite closely. The core is approximately circular. The assemblies are supported on a diagrid. The fuel assemblies can be replaced while the reactor is at power by withdrawing the fuel assembly vertically with a vertical lift crane, which critically never touches the molten salt. Having a handling mechanism which has to go into the molten salt, as is done with sodium fast reactors with sodium, is a problem because it makes the mechanical failure of a lifting mechanism much more likely. A fuel assembly is taken out and then replaced. The ones that have been taken out are moved to the periphery of the reactor tank, where they decay for up to a year, and then removed as a batch through the airlock of the reactor into transport flasks for storage, disposal, or far preferably reprocessing through a mechanism which I will describe a little bit later. So now I'd like to talk about the fuel cycle. No use having a nuclear reactor if you don't have fuel for it. The SSR-W is fueled with reactor grade plutonium and higher actinides recovered from existing spent nuclear fuel. And as everybody knows, reprocessing is a commercially non-viable proposition. Nobody's ever made it make economic sense. And we're not into commercially non-viable propositions in Moltex. So the fuel cycle is important to us. So let me talk about reprocessing. Conventional reprocessing using variants of the Purex process is based on technology designed to produce weapons grade plutonium. That's for its purpose. And it does it very well. it produces plutonium of extremely high purity, well north of 99.5% purity. And in fact, if you're going to make MOX fuel for commercial reasons, you actually need that kind of purity. Those fuel pellets have to be very, very high specification, for all the reasons I said earlier on in this talk. For that, you need high purity plutonium. SSR fuel does not require high purity plutonium. In fact, it doesn't particularly want it. The plutonium for the SSR can be contaminated with more than its own volume of uranium, and it can contain quite a substantial amount of lanthanides, which is important because the lanthanides are the chemical which is actually quite hard to separate from plutonium. We don't separate it. So, the fact that we can tolerate this really very low purity plutonium opens up options for reprocessing which just don't exist without the SSR-W reactor. And this, on one slide, is our process, we call it WATSS, for converting waste into stable salt fuel. The input is can-do spent fuel bundles. These contain about 20 kilograms of uranium. They have quite a low level of plutonium, about a little under 0.4%, which is lower than most because can-do fuel is low burn-up. But for us, it's absolutely fine. We take these bundles clad in zircaloy. First step is we declad them using chlorine gas, a technology which was pioneered and demonstrated in the Earth's laboratories. This produces zirconium tetrachloride as a one output, small amounts of gaseous waste from the pressurization gases, and pellets, uranium oxide pellets. Those pellets are fed into an electro-reducer, and the key novelty here is we don't simply reduce the pellets to uranium, we also add iron to the system. So they're actually reduced to a uranium iron alloy. That's important because uranium iron alloys melt at about 725 degrees centigrade, whereas uranium melts at 1100 plus. And so it is a far, far more practical proposition reducing at that temperature range. The output from the electroreducer is a uranium iron alloy which also contains the plutonium and higher actinides, a fraction of the lanthanides, all of the noble metal fission products, and pretty much nothing else. The waste product from the electroreducer is a very concentrated electrolyte containing most of the radioactive fission products. The third step is to take that uranium alloy and to extract it by contacting it with a clean salt mixture containing an iron salt. The iron exchanges with the plutonium and the lanthanides and a small amount of the uranium in the alloy, extracts those actinides into the salt. A single contact will remove, or is predicted to remove, more than 98% of both the plutonium and americium into the salt. In our design we have 2 successive contacts, so we recover essentially all of the higher actinides into the salt. Looked at in overall terms, what this process does, it converts about 99% by weight of the spent fuel into a uranium iron alloy. This has essentially no decay heat, minimal radioactivity. It could be disposed of as intermediate level waste, or it can be stored at surface locations for future use. It contains uranium. At some point uranium is going to become a valuable material. It will be a store of value for the future. The process produces about 0.4% of the weight of the spent fuel as our fuel, steel stable salt reactor, and it produces about 0.7% by weight of a high level waste which contains most of the reactor fission products but has a relatively short hazardous life because it is essentially completely actinide free. Storage or disposal of that is something which will be new to the nuclear industry, but is an intrinsically less difficult thing to achieve than for the original spent fuel. I'd like to now talk about third key technology in the Moltex proposition. We call this grid reserve, and this is cheap gigawatt hour scale energy storage. Going back to the slide I showed earlier, the real thing we need to achieve is economic operation at something like 30 to 50% capacity factor. And that is something which is challenging, but essential given the way electricity markets are evolving. Fortunately, the technology is actually already out there. Thermal energy storage has been pioneered in the concentrated solar power industry. The picture here is a concentrated solar power plant, mirrors in the desert, which is a wonderful system. It produces really good, high quality, high temperature heat around noon, when nobody really wants the power. And so this industry has pioneered storing thermal energy in large amounts so that you can store the midday energy and use it to produce electricity when people want it, which is often early evening. The technology used for that is actually a molten salt. Pure coincidence, but it is a molten salt. It's molten nitrate salts, and it is a very cheap, very practical and well proven technology now. The picture on the bottom right of the screen actually shows the molten salt storage tanks associated with a solar power station. What we're using is essentially exactly the same. This slide shows how we intend to deploy the SSR reactor. We would have a 500 megawatt output reactor, 500 megawatt electric, so about 1250 megawatt thermal. That heat output goes into the grid reserve thermal storage tanks, and those will feed boilers and turbines in our base case design at 3 times the power capacity of the reactor. So we have a 500 megawatt reactor driving a 1500 megawatt power station. Economically, this is very important. The graph here shows the wholesale price electricity in the UK. The UK is a really very free market electricity system. It's highly competitive. It has a properly commercially determined price of power. And that price varies a lot over the day. So our model would be we would charge up grid reserve and not produce any electricity during the periods of the day when the electricity would have least value, and then we sell the power during the periods when the electricity will have the greatest value. Looking at the numbers, and again this is for the UK, every country will be different. In the UK, over the 3-year period 2017 to 2019, the system selling price averaged over the whole period was £47 per megawatt hour. If you just sold your electricity into the best 8 hours of each day, then that same electricity is worth £70 per megawatt hour. That's a premium of £23 per megawatt hour at a cost of adding in the grid reserve and the greater turbine capacity of about £7 per megawatt hour. It is an economic and business no-brainer to do this. It also has an interesting side effect on the economics of the system. Advanced nuclear technology, new technology, in fact all nuclear technology is high risk economically because nuclear energy has been known to have cost overruns every now and again. And investors are nervous because of that. The consequence of adding triple capacity turbines and grid reserve to the power plant is that the fraction of the total power plant cost, which is the nuclear bit, is relatively low. It's around about 40%. This means that if you have errors, and everybody has errors in their assessment of nuclear costs, they don't make that much of a difference. So if that nuclear cost doubled, the impact on the overall capital cost is only about 25%. That brings the risk factor in building nuclear down really very substantially. So pulling this together, what does this mean? The economic benefits are, first of all, doing your safety right. Eliminate the hazards. Don't try to engineer solutions to those hazards. And secondly, use grid reserve so that you produce your power at the right time and you reduce the nuclear fraction of your power plant cost. This is the graph I showed before, showing how power plant costs have escalated over the last 40 or so years. The stable salt reactor is at the end there. This is in the configuration where it has a 1,500 megawatt output and a 500 megawatt reactor. And you're looking at costs around $1,000 per kilowatt. That is extraordinary. It is extraordinary. Most important, you could triple the nuclear cost and still be very, very comfortably within the $2,000 to $3,000 region where you need to be for financial viability. This is enormously important commercially. It reduces the risk of the investment by a very large factor. So let me just summarize. The concept of putting molten salt fuel in essentially conventional fuel assemblies is a genuinely new concept. It eliminates a large number of the difficult engineering challenges that molten salt reactors face. The low nuclear island cost itself, coupled with the fact the nuclear island is a relatively small part of the total cost, reduces the overall capital cost well below $2,000 per kilowatt, using conservative assumptions for optimism bias on our costs, with a really quite high confidence that that cost will not be exceeded. Thirdly, grid reserve, thermal energy storage, which I regret is available to everybody. I'd love it if we had that patented, we don't. Grid reserve makes nuclear energy a real partner to renewables in a market where renewables can produce electricity at essentially zero marginal cost. Energy storage is essential for commercial viability, and thermal energy storage is the way to achieve that. And finally, and far from least, the SSR-W, the Wasteburner reactor, can detoxify the legacy waste from the first nuclear era. That is something which is really quite important to developing the social license for nuclear in more countries. People worry a lot about nuclear waste. A solution to that which reduces its longevity and cost and potential impact on future generations goes a long way to make people accept nuclear energy. So I'll end there. Many thanks for your attention, and I hope you enjoyed the talk.